We're looking at section 8.1, which is graphing simple rational functions. So we're going to be graphing these functions as well as identifying asymptotes and showing the end behavior. So the first thing you want to do is we want to graph the parent function of 1 over x. So this is a good thing to do. Grab out your calculator and graph 1 divided by x. So this looks a little funky, as you can see. If you go to the table, we can open it. There it goes. One thing you'll notice is that there's lots of decimals here on your y's. The only whole number points we have are actually located at -1, -1, and at 1, 1. You'll notice there's an error at 0. So what this is telling us, that arrow at 0, that's having to do with our domain and our range. So first of all, we can graph the point 1, 1 and -1, 1, as well as the general shape of what was going on in our picture. Looks something like that. So when we're dealing with these rational functions, our domain and range are going to be implied being all real numbers. We're more looking for where are the problem areas. Where can the function not exist? So in this case, you'll notice that that error was at 0. And so what this is telling us is that for a domain, x cannot be equal to 0. That's why we had an error. Same thing is true for the y. Range. Y cannot be equal to 0. You'll notice that we have what are called some asymptotes. Asymptote is a line that your function always is heading towards, but it never actually is going to get there. You'll notice in the graph, the y values are always coming up here closer and closer to 0. That's telling us our horizontal asymptote. We've got a horizontal asymptote at y equals 0, the x-axis. And our x values, they're getting closer and closer here to 0, but they're never going to quite reach them. So we also have a vertical asymptote at x equals 0. So when we label asymptotes, we usually draw a dotted line in those areas to show that's where the asymptote is located. End behavior, we look at two places. We look as x goes to positive infinity. What are the y's doing? Well, as we move to the right in the graph, the y's are all headed towards 0. They're headed toward that horizontal asymptote. And as x goes to negative infinity, it's the left side of the graph. What are the y's doing? Well, they're going to the same spot. They're going to get 0. They're getting kind of stuck there at that horizontal asymptote. We're going to ignore odd, even, and either, increasing and decreasing. So increasing and decreasing, we're looking at are the y values getting bigger or smaller as we move along our graph. So since our graph is kind of disjointed here, if you look on the left side here, you notice y values are getting smaller and smaller and, they're getting smaller, which means they're decreasing. The y values are never getting bigger, so they're always decreasing. On the right-hand side of our disjunction here, y values are also getting smaller and smaller and smaller, so it's decreasing there. So our function is never increasing. The y values are never actually getting bigger. But it's decreasing, it's in two spots. Remember, we're disjointed because of that asymptote. So it's going to be decreasing from negative infinity to 0 and from 0 to positive infinity. When we graph these simple rational functions, we've just graphed the parent function here. We have the vertical and horizontal asymptotes. We also have those reference points. Those are the 2 points that we knew for sure were points. When we graph these, we like to ignore the 1 over b, the horizontal structure compression, but these act the same way as the other transformations we have seen. It's the same types of transformations, just a different start to our graph. So for example, in the denominator here, kind of inside the function, that's what's happening to our x values. That's actually going to tell us where the vertical asymptote is. It's telling us the how much we're shifting left or right. Outside the function, the k is telling us our horizontal asymptote because it's telling us where we're shifting up or down. A is still going to be telling us if it's a negative, that means we're doing the reflection across the x-axis. And if it's a number bigger than 1, that's when we're doing a stretch. And if it's a fractional amount, that's when we're doing the compression. And then we'll use these reference points to apply the changes based on what the function is doing. So let's try one of these out. first thing to look for are the translations. So where are we shifting, left or right? So in the denominator, that's what's telling us our horizontal shifts. So since it's a -1, we're actually moving to the right one. That's the one that's kind of backwards in our mind. Then outside the function is telling us where we're shifting up or down. Because it's addition, we're going up 2. If it's a reflection, we should be multiplying by a negative, and we're not. So there's no reflection. And then the 3 is giving us our dilation. So that's going to be a stretch of 3. So our vertical asymptote is based off of that horizontal stretch, or our horizontal translation. Since our function is moving to the right 1, our asymptote will be at x equals 1. It's going to have shifted to the right 1. Our horizontal asymptote is going to be y equals 2 because we've shifted up 2. So when we draw those asymptotes on the graph, again, you like to draw them as a dotted line, just so we can use them as a guideline, but they don't actually exist. We'll have horizontal or a vertical asymptote at x equals 1 and a horizontal at y equals 2. So that's showing us kind of where our axes have shifted. Domain and range, again, those are based off of the asymptotes. Those are where things can't exist. So our domain is that x cannot be equal to 1 and y cannot be equal to 2. Everything else is assumed to be all real numbers. So when we think about how do we graph this, well, we have to use those reference points. So we want to see what the function is doing to those. So the x minus 1 is just what's doing the right shift. So that means our x values will need to add 1. The 3 multiplying by the 3, and then the adding the 2, those are affecting the y values. So we'll need to multiply the y values by 3 and then add 2 to do the up shift. So that means the coordinate that was originally -1, -1 will change to 0, -1. And the point that was 1, 1 changes to 2, 5. So now we can graph those points, 0, -1, 2, 5. It's up here. And then just graph the basic shape of our function. So it's going to look something like that. Let's do another one. So we want to identify the transformations and state the asymptotes. So before we start, I'm going to go ahead and pull out this as a fraction, just so it looks a little more familiar to how we've seen before. So now we can see what our transformations are. So +3 in the denominator is telling us we're shifting left 3. -1 on the outside is telling us we're shifting down 1. We're not multiplying by a negative, so there should not be any reflection. And that multiplying by 1/2 on the outside is telling us we're going to do a compression by 1/2. So our vertical asymptote will be at x equals -3 because of the left shift. Horizontal asymptote will be at y equals -1 because of the downward shift. So then our domain, x can't be -3, y can't be -1. We can draw in our asymptotes at -3 and at -1, kind of showing us our shift. So now we can see what's happening to our reference points. Our x values are shifting left 3, so you'll need to subtract 3. Our y values will need to multiply by 1/2 and then subtract the 1 for the downshift. So the reference point -1, -1 will move to -4, -1.5. Reference point of 1, 1 is going to move to -2, -1/2. So we can graph those points. -4, 1, 2, 3, 4, -1.5. So that's about there. -2, -1/2, about there. And then we draw the general shape following the guidelines of those asymptotes in our picture.